statement that energy cannot be created or destroyed. So this concept is what we call the conservation of energy. Now, if we look at the first law, we can state that from the first law of thermodynamics, we say the net work done is equal to the net heat supplied and from this concept, since the intrinsic energy, is unchanged, we can write that the cyclic integral of dq is equal to the cyclic integral of dw. So we are taking this cyclic integral for a process, for a circle. So it is good to also state that while we discuss the concept of the first law of thermodynamics, we should also state that this concept cannot be proved analytically, but through experimental evidence we have continued to see and confirm that this law holds true repeatedly. So this experimental evidence shows its validity. And since no principle has been shown to contradict the first law of thermodynamics, it has therefore been accepted as a law of nature. Now, the first law of thermodynamics doesn't only apply to reversible processes or systems, it also applies to irreversible processes or systems. Here, we will start to discuss in this next section what we call the PMM1, that is the perpetual motion machine of the first kind. Now, to write into that statement, we would first of all think about why do we have that concept. We have the concept because it is stated that no machine can produce energy without corresponding expenditure of energy. No machine can produce energy without continuous expenditure of energy. So, I will pick up a few sections before the end of the class, but I want to specify some things that we can get from experimental studies about the first law. The first of that thing is a definite quantity of work is always required to accomplish the same temperature rise obtained with a unit amount of heat. The second statement we can get is regardless of whether the temperature of the liquid is raised by work transfer or by heat transfer, the liquid can be returned by heat transfer in opposite direction to the identical state from which it started. So these two things have been seen from experiment. Experiment has shown these two concepts. Now, we want to discuss the relationship between these two forms of energy, the work and the heat. We can relate these two forms of energies in the following equation: that the cyclic integral of the dW is equal to J, some proportionality constant, times the cyclic integral of the Q, where J is the proportionality constant, which we call the mechanical equivalent of heat. Now, I can write that the change in energy of the system, that is E2 minus E1, should be equal to Q minus W, the heat and the work. I can write further that the delta E can be represented by Q minus work. I can therefore solve this to get the state points from state 1 to 2. I should integrate the differential of the Q minus the W. So if I do that, I can write integral from 1 to 2 of the Q minus the W should be equal to delta E. So I can write this full equation in this form, which is also equal to E2 minus E1. Where this E that we've been using, E represents the total internal energy. So, if we have electric, magnetic, chemical energies absent and changes in potential and kinetic energy for a closed system, if we neglect all those forms of energy, we can then write the above equation, that the integral from 1 to 2, the Q minus W, is equal to the change in internal energy, which is written as U2 minus U1. So, now we've discussed energy, and we discussed that there is similarity between the heat and the work energy based on the fact that they cannot be referred to as state, but they have no meaning when you refer to them as state. Okay? Now we want to now discuss this concept of energy. Are they a property of the system? So, and we take point 1 and point 2. This is part L, this is part M, and this is part N. Now, I go from state 1 to 2 through the part L, and I'm coming back through either part M or N. I want to find out the energy quantity when I come through part N or the energy quantity when I come through part N. Are they the same quantity? Does my energy depend on the part I take? So with that, we'll be able to decipher whether energy is a property of a system. So if we want to do that now, I'm going to write our equation as integral dW is equal to second integral dQ. Now, I'm going to sum both the work done taking part 1 and part N. So let's considering L part N. So I will have the work done due to L plus the work done due to N is equal to the sum of the heat, which is Q due to L plus Q due to N. Now, this total process constitutes the circle. So if I would write QL minus WL. I'm taking all the L's to one side and all the M's to the other side. So if I also take this one, I would have that WN minus QN. Now, these two terms, this term represents the change in energy for part L, and this is representing, of course, it has a negative sign, the change in energy in part N. Okay. Say we follow part N instead. So we can do the same formulation similarly. For part N, we have delta L, delta EL similarly is equal to minus delta EN. So all I needed to do was to replace all the N's with N, and I arrive at the same thing because it's the same energy balance. So if I do that, I obtain this equation. Now, I can therefore see that negative En is equal to negative En. So if I can write this, then that means that for whichever part I take, either M or N, I have the same energy quantity. So we can write the following statements: that the change in energy between two states is the same. Whatever part the system may follow in undergoing that change of state, in undergoing that change of state. Therefore, we can say that energy has a definite value for every state of the system. Hence, energy is a point function and a property of the system. Having said that, we now go to that nice and interesting discussion we want to pick up about the PMM1, that is the perpetual motion machine.